So that's precisely what we would like to do. Precisely what we would like to do in the higher dimension. Okay. So let's see how to do it. This type of differentiation is called the Frechet differentiation. So the next thing is to define Frechet derivative. Okay. But engineers like to call it total derivative. I like to call it a Frechet derivative. This is good. That's a perfect and an excellent question actually, because the moment you started realizing that the curves are giving you the better approximation to the curve, then why to stick to the line? You created something called the Maclaurin series actually, or the Taylor series, because Taylor series is a way to approximate the curves through the curves actually. So you are already doing it. When you learn Taylor series, basically you are doing what? You are doing that, okay, you have a function, okay, some crazy function, and you want to find a polynomial. If you plot the polynomial, that would be curve, okay, but that curve is approximating your crazy function in a small interval. So you do it, okay. So maybe if there will be time, we will also talk about what would be the Taylor series in higher dimension. So you have also Taylor series in higher dimension. Why you can't have it? You can have it. You can have everything that you have in one dimension in higher dimension, but in a more sophisticated manner. It's a very good and natural question. Okay, so we like to begin with by differentiating the functions that are scalar valued. Okay. Then we will talk about the derivative of the vector value. And it's a natural way. So why I want to start with a scalar valued? I want to differentiate first scalar valued functions. By scalar valued functions means map from Rn to R actually. Okay. So when the outputs are R. And then I would like to compute the derivative of the vector valued functions. Okay. The functions where the outputs contains the components, where each component is a function. The answer is, I would like to do something similar that we did in the first chapter. For example, first we started with that how to compute the limit of such kind of functions. As x, y goes to 1, 2. And then in the next, we said that of x, y is say x square plus y square and xy. So how to compute the limit of such functions?
Again, same procedure.
The procedure is same actually, because its component are scalar valued. Okay. So whatever the limit of this function and this function is going to be, as xy goes to 1, 2, okay, the limit of this function is going to be the vector consisting of this limit and this limit. Okay, are you getting the point? So if x square plus y square goes to 5, so if this goes to 5 and this goes to 2, then the function goes to 5, 2 as x goes to 2. Okay, so we did this. So what do you want to do? So first I would like to differentiate such kind of functions. Then I would like to prove a theorem that tells me that if you want to differentiate such kind of function, differentiate this and then make a vector out of it. So that will be the derivative of this function. So that's what I would like to do. Isn't it? So therefore I am starting with scalar valued functions. So consider the Frechet derivative, okay, the total derivative of scalar valued function. Consider a function from U to R. Okay? And where U is the open subset of Rn. It's an open subset of Rn. So I need to what? I need a point where I want to differentiate things. So that's A is a point in U and H, writing explicitly H1, H2, Hn is also a point in Rn, or a vector basically. It's a vector in Rn. Position like the corresponding to it. Okay. So A is the fixed point. So I have this region. So this is the domain of it. So here I have A, and obviously corresponding to this I'm going to have f of A. Okay. Then I want to move away from A actually. Okay. I want to move away from A. So interestingly, now I have many directions. Like for example, for the derivative, you have the left hand and right hand derivative. Now you have many derivatives. You can go in any arbitrary direction. So where would be A plus H? It could be anywhere. So A plus H is something like this. So if I have A plus H, so I'm going to have and A plus H as well. Anyway. So that's what we would like to do. Then what is our aim? Our aim is to find the linear approximation of f at okay. Must be linear. Okay? This is what that is. And if it is linear, how does it going to look like? So what was the linear approximation here? How does the linear approximation should look like? So in one dimension, the linear approximation was, say, f of A plus lambda h. It was of this format. Okay. So if I say, what should be the linear approximation in higher dimension, then what do you think what should be the linear approximation? Huh? So it should be f of A. Okay. There I have only one h, but now I have components actually. Okay. So it should be of the form lambda h1 h1 yes, lambda to h2 and lambda and hn. So it should be of something like this format. So that's what we will like to find. Okay? I am calling this a quantity L of h. So it's a linear expression depending on the h. Okay? So I'm just giving it a name. नाम देने का हक है ना भाई? Maybe it's born I can give it a name actually. So I'm giving it a name. So I want such kind of an approximation. So that's what is my objective. So how to do it? I'm going to play the same game. Let's see that whether the same game works or not. Okay? Remember, computation is not a difficult thing. If you want to learn this computationally, it's not difficult. The real thing is developing the theory. Okay? So developing the theory in a consistent manner in such a way that it should make sense that why you are, so if I have one definition, why do I have another definition? What was missing actually? That is kind of So what should we do? How can I find the error? So if I want to find the error for f, function f, lambda, okay, and so I can start again with that. Okay, so take the f of x, okay, but now this f of x is in higher dimension and x is a vector, and subtract what? You know, this f of a plus vector lambda. I can have a vector lambda times dot product with the x minus a. Okay, so x is a vector and a is also a vector. So lambda, so I'm taking the dot product of lambda times x minus a. And I can give this x minus a the name h. Okay, so the h is this, what do you call it, difference. So the output is going to be this f of x minus f of a plus lambda dot x minus a, and since x is, you know, h is x minus a, so I can have f of a plus h, okay, and minus, what do you call this entire expression that you have, okay, the linear approximation of f of
lambda x होगा lambda x ना देगा वैल्यू दे रखेंगे h.
Yes, so that's what I want. So I'm going to have f of a plus h minus f of a plus L of h plus L of h actually. Okay? And this is error. E, f, lambda, a and h. Okay? E, f, lambda and h. So if I wish, I could directly define error to be this. Okay, so the error is what? You have a point on the surface and you move to another point and then you want to see the difference and you want to approximate that difference by something that is linear. Okay? And this difference is basically of this form, and we call this as, what do you call it?
ये माइनस जब अंदर मल्टीप्लाई होगा तो वो लैम्डा के साथ माइनस नहीं आ जाएगा?
किसके साथ? अच्छा ठीक है, वो
और सर लैम्डा h नहीं होगा ये?
हाँ?
लैम्डा h समझ नहीं आता.
Let's do it this way. Here's the thing. So I am in 3 dimension. Okay, so that's my u. Okay, that's my surface S. Map actually. So this is the plot of what? So x, y, and f of x, y. That's the plot of this x, y, f of x. Okay. Then I have a point A here. It's going to have a corresponding point f of A. Here. That's going to be f of A. So what I want to find something linear, okay, that approximates that surface around this point. Okay, that's what it's like. Then I'm saying that, okay, I moved a little bit and I reached to another point, you know, to which I can describe it as a plus h. So I'm going to have another point a plus f of a plus h actually, and something like that. Okay, and I want to, you know, I want to bring these points, you know, closer in such a way that I can have a best approximation. So So I'll be happy with this expression. This expression. So that's my function evaluated at a point x. Okay, and x is what point? So x is. I can give this, this new point as an arbitrary point away from a as a name x. So that's my x. So if x is a plus h, then x minus a is h. So what I want to do, I want to approximate my function by something linear. So I did the usual steps with the previous notation, and what we have f of a plus h minus f of a minus something linear, L of h. And what is L of h? I just defined it there actually. It's lambda times x minus a, where the x minus a is h. And then, as in the case of the one dimension, I gave this quantity the name error. Okay? And what I want to do, okay, so what I want to do, I want this error to go to 0. Okay? Not only to go to 0, but I want it to go to 0 rapidly. So if you want this error to go to 0 rapidly, what you need to do? You need to differentiate, not differentiate, but you need to, take E, F, this error, AH, and divide it by, norm of H, not H actually, because there is no meaning of dividing something by, vector. So that's what I would like to do. So when this would go to 0, and what would be the mean if I write this explicitly? When h goes to 0, so this would be f of a plus h minus f of a, minus this L of h divided by, what do you say, this norm of h. Okay, so I want this quantity to go to 0h. And I want this quantity to go to 0. Okay. So where would be my derivative hidden actually? So my derivative, is somewhere here actually. It's hidden here. Like in the case of one dimension, it was hidden in lambda. Okay, we need to take it out explicitly. Okay. So here's the thing. If you want to compute the derivative of a scalar function from Rn to R, okay, compute this limit. Okay, compute this limit. And how are you going to compute this limit? Compute f of a plus h, f of a, and this is something unknown that we are interested in. Okay, and divide everything by h. Okay, and when you will compute it, on the other side you're going to have this kind of an expression, and then take limit h goes to 0. So when this would go to 0, this quantity would go to 0, this difference would also go to 0. And once this difference goes to 0, this is your derivative, Frechet derivative of the function a evaluated at a point h. This is your Frechet derivative that you would like to find. Okay. I'm going to use this strange notation. Why I'm using this strange notation? Because this df of a, I'm saying that it's linear, but it's not only linear, but it's a linear transformation actually. So So if it's a linear transformation, so it must be from where to where. So it must be a linear transformation from Rn to Rn. So it must operate on a vector on Rn. So therefore I'm substituting h into it. That okay, that's a linear transformation working on n actually. So in other words, so for me the substitute for this L is this df of a. The df of a is what? The derivative, Frechet derivative of a function at the point A. But the Frechet derivative of the function at the point A is a linear transformation. It's a linear transformation. Am I getting the point? That's what we like to do.
Sir,
Let me quickly do one example and then we'll
Frechet derivative of function at point A, h to careless
they actually can. So like this expression, so I mean you remember the expression that was here in one-dimensional case was only dependent on h, but it was also dependent on a actually. Okay. So h should be there. For this L, I'm going to denote it. Okay, I'm going to give it a new name that I like. That is this df of a. So the df of a is a name given to this linear operator actually. That is operating on potential. Okay, and this name or this L that you have is what you call the Frechet derivative. Okay, so let's compute the Frechet derivative. So let's do one example. Okay, quickly. Concrete example. This is not a difficult thing. Very easy thing. So we'll talk further about it in the next discussion, but at least I would like to do one example of how to find this mysterious point. So let's take the same function. Let's take the same function which didn't work in our previous case. Let's see that whether we can, differentiate it now at any point A actually. A. So you can give me a point. You can give me 1, 2, 2, 1, whatever. But I want to keep it abstract. A1, A2. Okay. And if you want to do this, what you need to do? You have to first compute f of a plus h and subtract f of a. And subtract f of a. So what would be f of a plus h? So a is like a1, a2 and h is like h1, h2. So it's going to be a1 plus h1 and a2 plus h2 minus f of a1, right? Then this would be same as a1 plus h1 minus a1 what? Just a1. So you're going to get what? h1 is now. Okay? From our abstract definition, what was f of a plus h minus f of a? So this was, something linear, that is my derivative, plus the error. Plus the error, right? Plus the error. EF lambda of h actually. Okay. Plus the error. But in our definition, what I need to do, I need to subtract this here and divide by mod of h, and this will be equal to mod of h. So we have something like this. But in nutshell, I must have f of a plus h. F of a plus h minus f of a must be something linear plus the error. And that linear thing should depend on what? H. And the error term should depend on what? So it can depend on f and lambda. And mainly it depends on a and h actually. Mainly it depends on a and h. But in this case now, interestingly, what I have computed? So when I computed f of a plus h minus f of a It turns out to be equal to only one term h1 actually. Now h1 is what? Is it, shall I treat it as L of h or shall I treat it as the error actually?
Left hand side.
On the left hand side. So if I compare this with this,
They are equal, sir.
uh,
Sir, ये left hand side.
ये equal है, but shall I treat h1 as error or shall I treat h1 as L of, it should be L of h actually. Why? Think about it. Because now if you divide by norm of h, and if I divide this by norm of h, and if this is error, and I take h goes to 0, I know this limit doesn't exist. So this can't be error. So this must be high L of h. So in other words, what can I do? So I have h1. So what can I do? So let's take f of a plus h minus f of a and subtract h1 and divide by the norm of h. And what you have on the other side remaining?
0.
0. So your error is 0 divided by the norm of h. So what I need to do now? Just take the limit. Okay? Take the limit that the norm of h goes to 0. So if norm of h goes to 0, I need to take also the limit norm of h goes to 0. But no matter where norm of h should go, this would go to 0 actually. So this will be equal to 0. Okay? Now, since this is the linear thing, the linear function, the linear expression, from which if you are subtracting this increment, okay, the error goes to 0. Not only goes to 0, but since you are dividing it by norm of h, it rapidly goes to 0. So that's your Frechet derivative. So how should be, what should be the, okay. So I have L, so I want some L, which when operated onto h, in other words, when it operated onto h, h1, h2, okay, should give me the outcome at h1 should give me what outcome? Should give me the outcome h1. Is it making sense? But can you realize this, what the heck this guy is? What's a linear function? The original function actually. Can you see? This is the original function actually. Is it? So this is like you are operating f on the h. Okay? So what do I mean from here? I mean from here that if I take f and compute its Frechet derivative at a point A, and so I'm going to have a linear operator, and I operate it onto h, I'm going to get f of h, right? Because L के लिए हमने बाद में ये notation इस्तेमाल की थी, that was the notation that we used actually. So in other words, and this is true for all h actually. So in other words, the derivative of function at the time A is basically equal to the same function. It's a function whose derivative is itself, and it makes sense. Do you think why it makes sense? So this function is already linear. This function is already linear. It's a plane actually. So what is the best linear thing that approximates that linear thing? You're going to say itself. You're going to say itself. So the best linear thing that approximates a linear thing. So what is the best approximation to a line?
A line.
The same line. So the answer is really as per our expectation that if you want to differentiate a linear function, you have what is called the same function. इसको थोड़ा समझ लेते हैं. बिल्कुल. So we'll do more examples. Don't worry about it. By definition and through other tools. Let's start it with one simple example. So whenever the trick of computing the Frechet derivative is this. Compute f of a plus h. Compute f of a. Compute their difference. Once you compute their difference, okay, this was an extreme case where you get, a very simple expression coming as an outcome. Yeah. If a is this, then and h is this, what